working with a new company, ThorCon Power, to develop molten salt reactors. And this is what the talk is about. It's about the two goals we have: advancing prosperity of people who are energy poor, and also checking global warming in the sense of not emitting any CO2. First, a quick summary of global warming. Here's a chart from Jim Hansen's Columbia University project that keeps track of world temperatures. Columbia University, you remember, used to be called King's College, but after the revolution that changed. It's going up. The question is, why is it going up? One answer is that, let's see, how do I get the next slide here? Come on, Bob. Just a second, please. It used to work. Hang on just a moment. I need to change to the next slide. There we go. The and I back there. There we go. CO2 is in fact increasing in the atmosphere. These are observations that you probably are familiar with, taken from an observatory in Hawaii. The question is, does CO2 somehow cause this to happen? We can only tell that through modeling. And here's, again, a model presentation in a paper by Jim Hansen that I actually edited and made a little more concise. So if you can quickly look for climate change in a nutshell sometime, you could locate it. In this graph, the observations you see are in the dark black line. The various models of what the temperature would be like are represented in the blue band. And they take away the human factors to show just what happens from things like precession of the Earth's axis of rotation and all those other sorts of things that many detractors claim are the real cause of global warming. You see that that's not sufficient to describe what's observed. So I personally think absolutely that man's CO2 contributions do contribute to global warming, and we'd like to stop that. There's been a great political hue and cry about trying to reduce them. And there was a meeting in Paris about, 5-6 years ago that claimed that nations were going to voluntarily reduce their contributions. Now, you look at the graph, which I took from the emissions graph report of the IPCC, and you'll see that business as usual, which is sort of what's happening now, is showing a rise in emissions into the atmosphere of about 65 gigatons per year. We'd already pledged 59 gigatons by 2030 with the Cancun meeting policies. The Paris pledges, in reality, only dropped the goal by about 3 gigatons per year. So although everyone decries Donald Trump and many others for not enforcing the Paris pledges, the answer is that that's only about 3 gigatons a year. We need to reduce CO2 emissions by an order of magnitude more in order to have the effect we want, and that is to reduce global warming. The other problem we have is that people really aren't following those guidelines that they pledged. One of the reasons, too, we should worry about is the need of the developing nations to increase their energy supplies to develop their own prosperity, similar to that in the EU or the US. This graph shows in the vertical dimension the per capita average electricity consumption in watts. So In North America, it's about 1,500 watts per capita. In the EU, about 700, China, 400. The horizontal dimension is the population of the region. So the big yellow area basically is the potential for growth in gigawatt hours of energy consumption per year. It's enormous. And look again, where we are going to be talking about Southeast Asia, average electricity energy consumption is only 75 watts. So they want more reliable energy that's inexpensive. And if you look at the various analyses of planned coal plants, there are about 600 gigawatts of coal-fired power plants that are being developed today and on the drawing boards in the next decade or two. If we added 600 gigawatts of coal plants, those together, which emit about maybe 800 megatons per coal plant, we'd be adding about 4 gigatons of CO2 per year. So far from reducing CO2 emissions, the developing nations are going to increase them. And if we can avoid that and also let them become prosperous, you'll have a much bigger impact than trying to squeeze down the emissions, which we should, but it's much more difficult. In the US, we sort of think we've ended coal, and UK has almost ended all its coal-fired electricity production. But here's where the real problem is going to exist. Again, here's a graph that was done plotting for each country as a blue dot, the relationship of per capita GDP to per capita electric power. And we see that a kilowatt of electricity is correlated to $4 to $6 of GDP per capita. There's a source here you can see, and another UK person, Ayers and War, did a book on the subject, which you can look at it as well. Very interesting. He's a guy who has applied thermodynamics to the world's population. So right now, the movement in the US and perhaps all of the EU, Germany for sure, is to say we can do this all with renewable energy. There's a Green New Deal idea in the US Congress. My questions are, what is the cost of that? And can it be scaled up? First thing to look at for a second is, what is the cost of renewable electricity, the cost of wind and solar, basically? And we have a kind of a naive perception in the press that somehow or other, this is a commodity that can be bought and sold like olive oil or coal or something. So we have the levelized cost of electricity, the dollars flowing towards a company that develops windmills or solar farms. And in return for those dollars, we get electricity. And that's a bit naive. The reality is the government has many, many rules and regulations. In the US, it's quite difficult because we have federal rules, but we also have a lot of independence in each state. So it gets more complicated as various groups of environmentalists recruit or join with the developers to basically change the rules of the electricity markets in the US. The first thing we have that you have as well, I think it's called feed-in tariffs, and that is, these give priority to a certain source. So for example, if you're built a wind or solar farm, you might get a feed-in tariff that says you'll be paid, pick a number, 20 cents a kilowatt hour whenever that power becomes available. That's a feed-in tariff. The one that people don't understand in the US well is the so-called renewable portfolio standard, where various states, like Massachusetts next door, pass a law that says that the utility companies must derive a certain fraction of their generated electricity from, let's say, solar. And that fraction might be 10%, 20%, whatever. There's typically a graduated schedule. What that means, in effect, is that they're mandated to get that much solar power or wind power. But if they don't have that capability in state to generate it, there is a whole market to buy renewable energy credits from other states that may not have such rules, but have generators who are willing to sell this quality standard. So a generator who has a wind farm or a solar farm gets paid not just for the electricity that's generated, but also for the renewable energy credits that he can sell, just like a kilowatt hour. He sells this fictitious quality certificate, if you will, that says my electricity is so good, you can satisfy your state mandate by buying them. The market for those is open. It's an auction market. And the costs run, at least in Massachusetts, 20 to 40 cents a kilowatt hour. Whereas from a natural gas plant, it might be 5 cents a kilowatt hour. So it's quite a premium. Around the circle, you see other things. When the developers, like let's say a nuclear power plant, are or could be paid for the so-called capacity reserve. That is the promise to say, I can provide electricity next winter at midnight. I promise to pay it. It's sort of like the capacity payments you might pay if you were trying to reserve space in a natural gas pipeline or something of that nature. By clever manipulation of the laws and so on, capacity reserve payments have been distorted to actually be paid to wind and solar developers as well, and so on. Credits for income tax, accelerated depreciation. There are many other complex subsidies, but they change all the time, and they change with the government body that's ruling. I mean, you can have a local, citywide property tax exemption, or you can have a state income tax credit, or you can have a federal production tax credit, and so on. So it's not a simple market. We have some friends at Stanford who came out with a book almost a year ago called A Cubic Mile of Oil. Rupu, who's a person I know, gave a talk, and I've stolen some of his slides with permission. And their idea was that people are not familiar with the concept of terawatt hours and so on in energy measures. And they came up with a new measure, a cubic mile of oil. They say that all the world's energy consumption right now would be achieved by burning literally 4 cubic miles of oil. So that's their new metric, if you will. And in their talk, they give some examples. The energy equivalent of burning a cubic mile of oil per year could be met by having 4.2 billion solar roofs. And here's his math. 2 kilowatt hours available 20% of the time. And if we built 250,000 roofs a year with solar power for 50 years, we could have enough solar roof energy generation capability to provide the equivalent energy of burning a cubic mile of oil. Same sort of argument with a solar park. Here's one, concentrated solar power, which focuses sunlight from mirrors onto a tower in the middle to heat molten salt, which then eventually heats water to steam to make power in the more normal way. We'd have to build 7,700 of those if we could do 3 a week for 50 years. It's just an enormous amount of work. How about doing a cubic mile of oil with a hydro facility? Well, here is an example of an 18 gigawatt hydro power plant. That's the capability of the Three Gorges Dam in China that took a decade or so to build and required the displacement of 1 million people. So if we could build one of those every quarter for 50 years, that would be the energy equivalent of 1 cubic mile of oil. Again, windmills, same idea. How many does it take? 1,200 a week for 50 years. Can we build that much wind and solar and water? So I said that the world energy consumption is about 4 cubic miles of oil per year. So if we did all those things that I went through, or that Ripu went through in his book, we might supply all the world's energy with all of these sources. But we have the intermittency problem that wind and solar are only available about 1/3 of the time. In the middle of the slide is an advertisement from a United States Gas Association. Natural gas is happy to have more wind and solar penetration because most of the time, the wind and solar is not providing power. It's backed up by natural gas, which is in fact a good partner because natural gas turbines can start up relatively quickly to provide power if there's an interruption due to some sort of a weather event. But in the United States, each gigawatt of wind and solar is matched by 3 gigawatts of natural gas, most of the time. Just in the last few days, they closed down a rather large nuclear power plant around New York City, and they've just built 3 natural gas plants in New Jersey to supply New York City's power. What about batteries? We're told the price of batteries is plummeting. It's going to drop as low as, who knows, $100 per kilowatt hour of capacity. But just think a minute. Suppose we said we're going to run the world on wind and solar, and we want to have a day of stored energy in batteries in case the wind and solar don't work for weather-related reasons. How much is that? Well, if we're burning, let's figure in our heads 400 days a year, 4 cubic miles of oil. Okay, so we need about 1% of a cubic mile of oil's worth of energy in order to back up wind and solar for just a day. Well, I went to the Tesla website, I looked up the size of the batteries and did the multiplication, and that's a cubic mile of batteries. Then I went to the site and I said, well, what is the cost of that? Well, you just do the math at 13.5 kilowatt hours per battery. If we built 1,000 per second for 10 years, we could back up wind and solar for a day at a cost of $231 trillion at the list price that Tesla is charging. So it's quite impractical. What about nuclear? Back to Ripu's talk again. He says, well, we'd have to build to generate 1 cubic mile of oil's worth of energy with nuclear power plants. We'd have to build 1 a week for 50 years. Well, that seems like a lot. People say, well, that's shocking. We can't do that. But I say, we can do that. And that's exactly what our company has been trying to do now for the last 5 years. We are designing and negotiating with builders and suppliers to build fission power plants of a size of 500 megawatts in shipyards, because it's an inexpensive way to do it. And we can then export those power plants to places such as Southeast Asia. Again, our objective here, cheaper than coal, otherwise people won't buy them. And 24/7, so we don't need to have backup when the weather changes. And it basically emit no CO2. Our founders have shipyard experience. They built the world's largest supertankers. They know engineering of large systems. They know the shipping industry. We have visited shipyards, gotten quotes, and so on. So we're guided by these principles, not just to build a new nuclear power plant, but to build one that's cheaper than coal. And we say, or don't bother. Cost is critical. If we need to convince people in Southeast Asia to not build coal plants, we need to have the plants that are fission plants, we need to have them less expensive than coal-fired power plants. We also need passive safety. We knew what happened at Fukushima. What happened was the safety depended on electrically powered systems that failed. So one of our objectives, in order to be able to convince people that these are safe plants, is to show and demonstrate that they're safe in power failures and they require no active systems to sort of take over if there's a problem. We also want operator independence. In the US, in a lot of places, there's a lot of emphasis on operator training, but operators can do the wrong things. At Chernobyl, the operators were explicitly told never to drop all those control rods at the same time, but they did. And they made many other operator errors. So we try to design a plant that is not dependent on any operator action for safety. Blackout safety. Again, if all power is lost, we still want the plant to be safe. We don't want to rely on electricity to run pumps, to run water, to cool decay heat. Last point on this side, molten salts have intrinsic safeties due to their low pressure, and which means that they cannot spew radioactive materials for miles in an explosion of some sort. And they also entrap radioactive isotopes of cesium, strontium, iodine, and so on that people are most concerned about. Those are dissolved in molten salt. And if they escape, they basically cool in the salt. We also want no evacuation zone. In a sense, it's the evacuation zone idea that killed over 1,000 people at Fukushima. Those people did not have to be moved, but people were frightened and the government moved them all. We want to be safer than coal, safer in the sense that particulate emissions kill really millions of people a year. We need to have 90% plus availability in order to satisfy the demands of the developing nations that can't be satisfied with wind and solar, but are satisfied with coal-fired plants. We want no new technology because we want to do this soon. We want to do this right away. We can't depend upon new R&D to come up with some magic solution like, let's say, fusion power plants. We also want them maintainable. And last but not least, our founder's goal, shipyard production, because shipyards are experienced and competitive in turning out large factories, literally, in quantity of high quality. So that's what we're looking to do. Now, a little bit of science just for a bit. Here's a description of how this system works. On the horizontal dimension are the atomic numbers of some of the elements, thorium through americium. And on the vertical direction are the atomic numbers, the weights, atomic weights. In the middle of the chart is uranium-235, a fissionable material, which if it splits, generates fission products and energy. And about 50% of the power of our reactor comes from splitting the uranium-235. Up above, you'll see uranium-238 in this diagram absorbing a neutron, becoming uranium-239, beta decaying in 2 steps to become plutonium-239 after a few days, which is also a fissile isotope, which becomes fuel, not just in our plant, but in every light water plant around the world. And in the bottom, same idea with thorium-232. It becomes a fissile isotope, uranium-233, and that provides approximately 25% of our fuel energy. Here's what the plant looks like top down on the rather large barge or hull. On the right-hand side are ponds that we use for passive decay heat cooling. The power plant, the nuclear part, the nuclear reactor part itself, we'll look at more closely in a minute, is the so-called fission island. And if you look to the left of that, there are power conversions loops that convert the hot molten salt heat eventually into steam that runs the rather large turbine generator. The turbine generator is by far the most expensive part of a power plant. It's big and it uses 100 years worth of technology to learn how to convert steam heat eventually to electricity that comes out through the switchgear on the left. The technology we use is based on Oak Ridge National Lab's prototype molten salt reactor that was demonstrated in the 1960s by Alvin Weinberg and others at that lab. In this example, the fuel is not solid, but the thorium and uranium is dissolved in a fluoride salt. In our case, it's a salt of beryllium fluoride and sodium fluoride. And so the thorium and uranium are also fluorides that are in this big bath, which is an unusual substance. It's really a bath of ions, fluoride ions, so sodium, beryllium, thorium, and uranium ions in a hot, perhaps 700-degree centigrade state. On the right-hand side, you can see about half of a cylinder of the core of their molten salt reactor being constructed. Those are graphite logs that have channels in them, and it's about half done. The molten salt, as it says, flows up through those channels. And the idea is that the graphite moderates or slows the neutrons that are created by fissioning the uranium or plutonium. So once the neutrons are slowed, they are more likely to cause a fission in a nearby U-235 or other fissile atom. When they're outside of the graphite, they're not going to create, they're not going to be moderated. We won't have any fission reaction. So fission only takes place when those molten salts carrying the fissile atoms flow through those graphite channels. Here's a sort of a cross-sectional view done by one of our consultants using software that simulates not just the neutronics, but also the heat transfer and the hydraulic flows of the molten salt coming up at you through the hex arrays of graphite channels. How that works is that graphite is in that yellow pot in this graph, and it flows upward. You can't see the pump in this picture through that orange pipe, crosses over in that red pipe, sorry, to the secondary loop, well, crosses over into a primary heat exchanger, the big blue tank on the right, and then back to the bottom and up through the pot again. It only supports fission while it is in the pot, and it heats up from something like 565 degrees coming into the pot at the bottom to 704 degrees centigrade coming out the top. I should say Celsius. I'm revealing my age. The heat exchanger removes the heat from the heated molten salt through a secondary loop, which is also molten salt, but without any fuel in it, without any thorium, without any uranium. So it's just a means of removing the heat from the big red can, which contains basically all the fuel salt within the can. It's all sealed within the can. Important numbers on the far right side are the idea of the pot pressure. The outlet pressure is only about 2.9 bar. That is 3 atmospheres of pressure. So it's not like a current light water reactor that has all the radioactive fuel in pressurized water at perhaps 150 atmospheres of pressure. The pressure is low, about the pressure of a garden hose. So in an accident, we don't have really a kind of an explosive force, just a modest force. Okay, next, the whole assembly sits in what we call a silo cold wall. Below that red pot, below the red can containing the pot and all the fuel salt is a series of cylinders that have a high surface area. It's the so-called fuel salt drain tank. If we have some sort of a situation occur, we want to turn this thing off in a simple way, we open the valve, so-called freeze valve, below the pot so that all the fuel in the molten salt falls into the fuel salt drain tanks cylinders below. The idea of that is that those cylinders have a high surface area, so they're good at radiating heat. Here, heat is our friend in a sense. The nominal operating temperature of the hottest salt is 700 degrees, but it can rise in temperature. And as you might remember, that the radiant heat increases with the 4th power of the absolute temperature. So the hotter it gets, the more capable we are of radiating heat across from that red can or from the green drain tanks across the little space to the silo cold wall, which is itself water cooled. It's cooled by water that changes perhaps to steam and rises to a cooling pond that you might have remembered in the very earlier slides. I'll show you that in a minute. So there's the idea there. The each of these cans is paired. We have an active can and a cool down can for each module, each power module. There are 2 power modules in a plant, each of which has the capability when it's running to generate 557 megawatts of thermal energy. And we'll talk about its conversion to electricity later. It runs 4 years, and then we basically move the fuel salt from one pot to its partner pot and let the can cool down. In the background, you can see the pipes that look rather U-shaped. They contain tubing, which are the heat exchangers. And we'll look at those again in a minute. Here's the schematic of what happens, how you, in our case, convert the heat energy to electricity. There are many molten salt loops. The pot we mentioned before, the yellow device inside the can, circulates through the PLP, the primary loop pump through the primary heat exchanger. That heat is exchanged to a secondary loop with a secondary loop pump that again transfers its heat to a third loop, and we can talk about that later. That is what we call solar salt. That's a mixture of sodium and potassium nitrate salts, the same as they are used in concentrated solar thermal power plants, which eventually generates 550 centigrade steam. This is very hot steam, hotter than in a normal light water reactor plant. It's the same temperature as in a supercritical steam coal-fired plant. From there, it goes to a basically a turbo generator that is identical to the kind of steam turbine generator used in a coal-fired plant. That means we get high efficiency from all this of conversion of thermal energy to electric power, almost 48% with a 20-degree seawater coolant. This is all embodied, that's a schematic. The reality is here in the plant CAD diagram. On the left, you see the orange pot inside the can. You can't really quite see the heat exchanger in the can. The green line contains the secondary salt, which transfers heat to the heat exchanger just above the figures that you can almost see there, the people, to the purple solar salt loop, which powers the steam generator, which makes that 550 centigrade steam that goes to a complicated turbine generator setup to achieve the high efficiency. So that's the guts of the transfer of heat from the primary loop created by fission off to the steam generator on the far right. Safety is important to us. We want people to understand that we can't have a problem that will cause a release of radioactive material that's dangerous. And so we have a lot of intrinsic safety principles. One is, oddly, working at a high temperature, we are in a regime in the salt where as the molten salt heats up and the uranium atoms heat up, or the fissile plutonium atoms heat up, they vibrate faster and faster. And that means that there's an increased chance that they're vibrating at just the right energy to hit one of the so-called Doppler resonances that absorbs the neutron. So U-238 vibrating can absorb the neutron and take it away from contribution to the fission process. There's another device too, and that has to do with the expansion of the fuel salt itself. Altogether, when you do all the physics, what happens basically is as the molten salt heats up, the chain reaction slows down. So there's this natural stability incorporated because of the fact that the materials are able to operate in liquid form at high temperatures, about 700 degrees. And there's no chance of them really vaporizing and changing state because the boiling point is up around 1500 degrees. Any break in the system will drain that molten fuel salt to the drain tank, and the operators have nothing to do with it. There's nothing they can do to stop this kind of drain from happening. Again, the silo cold wall we mentioned before, we'll show a picture of that again, is the heat is passively removed. There's no pump or anything that basically cools that cooling wall. In this picture, you can see the blue cooling wall, the silo wall, is basically connected to the cooling pond by water that flows through convection to a condenser sitting at the bottom of the cooling pond, which slowly heats up and causes evaporative cooling to the atmosphere. So there's no pumps, no operator controls, no valves, nothing. In our design, we give up some efficiency beyond always letting that convection take place, whether we're in a safety recovery state or just normal operation. One of the important things is to be cheaper than coal. And that's a little hard to do. But we are cheaper because the plant can be much smaller. The capital costs for a coal-fired plant being built today run about $1 to $2 per watt of capacity, $1,000 to $2,000 per kilowatt of generation capacity. Roughly, a considerable amount more than the cost for a ThorCon power plant. Fuel costs are what the big difference is. Uranium is, what, 1 million times more energy dense than coal. And so even though it might be a little more expensive to mine than coal, the fuel costs for a uranium fuel plant are about ½ cent per kilowatt hour. And the electricity costs are less. 3 cents, we believe, is quite feasible compared to a new build coal-fired plant today, about 5 cents per kilowatt hour. Again, a picture. Coal plants are big because the energy density of the coal is low compared to that of uranium. And the capital cost of a coal plant is larger because it's such a big plant. It has to handle so much coal and ash. That's the intrinsic basic reason we can make energy cheaper than coal. The energy density of uranium is A, the fuel cost is less, and B, the capital cost is less because we don't have to handle so much fuel. The plan is to build this plant, and it's built in a hull, in a shipyard in the Far East, and transit it, tow it, if you will, to a site. We expect it to be in Indonesia. Indonesia needs already about 20 gigawatts more electric power. They know it. We're on pretty good terms with people in the government. And so we're working together with them to go over all the hurdles that are necessary to get such a plant authorized to be installed. Again, back to our original point is that with shipyard production, we can generate 3,000 gigawatts of power plants over the next 30 years. That's the current power output of all the world's electric power plants on average. It's got to be cheaper than coal. It's got to run reliably 24 hours a day. And by not emitting CO2, we can address the global warming issue. Again, our benefits are what we have set out to do. We think we have achieved all of these benefits in the design. So let me take a break here, stop sharing the screen, and ask for questions.
Okay, thanks, Bob. I'll turn people on. Hang on a second. I've got to find out where to do that.